everyone, this is Kun of ETAP. I'm here today to talk to you about exploring ZSI protection scheme with advanced graphical interlock. In recent years, there has been a growing interest in the use of ZSI protection schemes for the protection of electrical networks. ZSI protection schemes are designed to provide a high level of protection against a wide range of faults, and they are particularly well suited for the protection of complex networks. In this presentation, I'll explore the use of ZSI, starting by introducing what is ZSI and what are the applications of ZSI, the ZSI wiring and interlocking, the ZSI manager and graphical interlock, and as well as how you can use ZSI for protection and coordination studies. What is ZSI? ZSI stands for Zone Selective Interlock. It's a protection scheme used with low voltage circuit breakers. It helps improving the protection of equipment by reducing the trip time. At the meantime, it won't sacrifice the coordination. ZSI can be used for detection of phase and ground faults. How does ZSI work? The upstream and downstream breakers has to be wired at first. When there's a fault happened, the downstream breaker sends a restraint signal to the upstream breakers. Upstream breakers receive the restraint signal and start restraint timer for tripping. The downstream breaker trips on unrestrained time if it's not self-restrained. Let's take a look at how it works on this ZSI wiring scheme. We have a green breaker, let's say this is A1. And we have an upstream breaker, the blue breaker, which is B1. So when we have a fault at this point, point A, A1 detects a fault, and now it sends a restraint signal through the output, and B1 received a restraint signal from the input, so it starts the restraint timer. At the meantime, the breaker A1 here trips based on unrestrained time, and then if the fault is not cleared, the upstream B1 will trip based on the restraint time. Based on the previous slide, we're saying A1 send a restraint signal to B1, and B1 will start the restraint timer, so you use the restraint setting for tripping. And A1 as downstream breaker will use the unrestrained setting for tripping. Let's take a look at what is restrained or unrestrained setting. From this star view, you can see the blue curve is unrestrained and the green curve is restrained. The restrained band typically is slower, which leading to longer trip time. In the unrestrained curve, the delay band is faster, leading to shorter trip time. That's why it guarantees A1 and B1 has proper coordination when the fault is detected at downstream of A1. Let's take a look at the ZSI settings available from different manufacturers. For most manufacturers, like Siemens, they don't have the adjustable ZSI settings. The ZSI is only available for short time and ground bands. So based on the fault and the restraint signal available, the unrestrained or restrained band will be used for determining the tripping time. For some other manufacturers like GE, they offer adjustable ZSI settings for the band as well as pickup. So the pickup adjustable settings for ZSI is called threshold. As you can see on this capture, the GE offers the short time band and the settings that you can select for the short time band ZSI If you want you can enable the instantaneous ZSI and also the threshold ZSI. It's fully customizable, so very useful. And when you want to define a ZSI wiring scheme for your specific application. ZSI wiring is the most important part for implementing the ZSI schemes. Each manufacturer has its own ZSI wiring scheme, and the ZSI terminals are breaker specific. You can have phase terminal, you can have ground terminal, or you can have the phase / ground terminal, which is the combined terminal between phase and ground. And for example, on this right side capture, you have the square DLE breakers. You can see the wiring schemes between the downstream and upstream breakers. The downstream breaker, they are jumped together, right? You see the output of the short time is jumped with the input. So this is the self-restraint wiring implemented for the downstream breaker. And also you see after jumping between the input and output, we are connecting this output to the input of the upstream input. And also for the ground terminal, you have a wiring sending the signal to the upstream. Also in this middle upstream breakers, the output signal is wired to the top upstream breakers. So that is the complete ZSI wiring scheme specifically for the square DLE breakers. So in this slide, we have two more examples for ZSI wiring. To the left, we have Siemens WL breakers, and we have 3 different zones, right? Zone 3, Zone 2, and Zone 1. And the breakers are interlocked between Zone 3, Zone 2, and Zone 1. And you can see the output terminals are connected to the input terminals. And on the right side, we have the color hammer breaker wiring schemes. You see there are different models from the color hammers. Some of them are having phase and ground separate terminals. Some of them just have the zone in, zone out, which is the phase / ground terminal combined into one. A new tool is designed and developed called ZSI Manager. This graphic interlocking display feature of ZSI Manager provides a central location for navigation, editing, and selection of the interlocks, as well as verification of entered data, visual verification of models, and arrow checking facilities. It also supports multiple one-line interlocks and submittal for installation. These interlocks allow users to easily and quickly configure the protection schemes, and they also provide a visual representation of the networks that can be used for troubleshooting as well. Now let's take a look at ETAP, that how we can display the graphic interlocks for ZSI scheme implementation. Now we have this project open. We have base revision and ZSI revision. In base revision, we don't have ZSI settings. We don't have ZSI wiring implemented. However, in ZSI revision, we have the ZSI model selected and the wiring are predefined. Now let's see how we can enable and see how the wiring scheme is implemented. Let's go to the right side toolbar and locate the ZSI Manager and Interlock Display button. Left click on this button will bring up the interface for the ZSI Interlock Manager and Graphic Display Editor. We have upstream breaker selection on the left side of this interface, and on the right side we are displaying the information of the highlighted breakers. And we have the breaker models, trip unit models displayed, and the wiring input output displayed, and also the interlock breakers from downstream displayed on the right side. Now let's go ahead and check the LVCB-main1. The right side tables updated based on the information available of LVCB-main1. And we can see three downstream breakers, LVCB-F1, LVCB-F2, and LVCB-F3 are interlocked with LVCB-main1. All of these downstream breakers have ZSI enabled, and all the output are phase/ground. Now let's go ahead and click display, and we can see the graphic interlocks are now displayed on the one-line diagram. ZSI Manager is modeless, which means you don't have to close the dialog in order to interact with your one-line diagram. You can simply highlight a breaker on your one-line diagram. The interlock display will automatically add it on your one-line diagram, and the ZSI Manager is automatically updated. Also, you can rubber band to deselect one or multiple elements from one-line diagram, and it will be removed from the one-line diagram as well as the ZSI Manager. The ZSI Manager is per presentation, which means you can implement to display different graphic interlocks per presentation. So here we are in OLV1, so you see the ZSI Manager title is for OLV1. I can check to display all graphic interlocks. Let me press OK. And now I'm opening another presentation, which is OLV2. And I can highlight the LVCB1 breaker, which I'm interested in. I just want to display the graphic interlock for LVCB1. I'm opening the ZSI Manager, and I see the LVCB1 is checked. I can check to display and press OK. Now you see I can have two different representations for the graphic interlocks for different applications. Maybe for OLV1, I'm interested to see all the graphical presentation. However, I want to focus on the ZSI implementation between LVCB main1 and LVCB1 in OLV2. To save your time, we added the shortcut for enabling and disabling the ZSI graphic interlock to the top toolbar. In OLV2, I can simply click on this button to disable my ZSI graphic interlocks. Also, we have implemented a complete theme that you can customize how the graphic interlock is displayed. In ZSI Manager, you can open the interlock theme, and we have the ZSI tab displayed from the theme editor. You can customize the graphic interlock per different output, phase, ground, phase/ground, or phase+ground. Or in case you have a breaker which does not have an output, ETAP will display the interlock with a color that you define here. With this tool, you can easily identify the issues you have for the interlocking that you can fix it later. And this is a great tool for troubleshooting the ZSI scheme implementation in your project. You can also customize the breaker box, the terminal colors, annotations, tooltips. Also, if you have a breaker which is interlocked to the upstream breaker from a composite network, and you can define how the interlock can be displayed on the one-line diagram. This theme is applied globally for all presentations. You can access this theme from the ZSI Manager, which I showed you right now. Also, you can close the ZSI Manager and access the ETAP theme from the theme editor right here. We have the ZSI tab added at the end of the theme editor. Now let's take a look at how we can do protection and coordination studies with ZSI enabled, and how the graphic interlock can help us to understand how ZSI works in our system. Let me close the OLV2, and now I have OLV1 open. I have the graphic interlock displayed. I'm having the proper study case selected, which is for ZSI three-phase fault. I'm go ahead and simulate a three-phase fault at the motor 1 terminal. We have the result displayed in the sequence of operation viewer. We can tell LVCB-F1 is tripping using the restraint phase curve. And we can easily identify from the graphic interlock that this breaker is self-restrained, so it receives a restraint signal after the fault is detected. So it easily explains why the restraint phase curve is used for tripping. Also, let me move the sequence viewer to the right side and click on the LVCB-main1. So you can see under the assumption that if LVCB-F1 is not able to clear the fault, LVCB-main1 will be tripping and is using the restraint phase curve. Right? This is based on the restraint signal sent from the LVCB-F1. So it will trip based on the restraint phase curve to have proper delay in order to have proper coordination between the downstream and upstream breaker. Now let's take a look how the curves is displayed in store view. I'm highlighting both of LVCB-F1 and LVCB-main1 and create a store view. So we have both curves plotted in a normalized store view, and based on the curve displayed, we can enable the settings for both curves. We can tell LVCB-F1 is the restraint curve, and LVCB-main1 is also the restraint curve. We can tell it has proper coordination, and we can verify the tripping time on top of the store view and compare with the sequence viewer. So this is the simulation at the motor terminal fault. So in this case, we have the ZSI implemented for coordination purpose. Now let's change the fault location to bus main 1. Let me move the fault and drop it on bus main 1. Now you see if the fault is happening on bus main 1, our LVCB main 1 is tripping way faster than what we had before, right? Now it takes 62 milliseconds, and the curve used for tripping of the fault is the ZSI phase unrestrained fault, right? And you can see from the normalized store view, and this is my LVCB-main 1, and I can enable the setting. It's showing the unrestrained curve is used. And typically unrestrained curve is the faster curve which we discussed. It has like faster delay for achieve the quick tripping. And this is what we can see when we are having a fault on the bus. We can achieve quick tripping using main. If the fault is at the load terminal or feeders, we can achieve proper coordination between downstream and upstream protected devices, especially for the breakers with ZSI interlocking schemes implemented. On top of that, we can see the LVCB-main 1 breaker is tripping and sending a restraint signal to LVCB1. So the restraint phase curve is used for LVCB-1. And we can create another star view by selecting both LVCB1 and LVCB-main1. So we can check we have proper coordination between LVCB-main1 and LVCB1 with the ZSI scheme implemented. Last, I'll show you how ArcFlash study can benefit from using ZSI schemes implemented. Let's close the sequence viewer, cancel the fault, close the star view, and switch to ArcFlash mode. In ArcFlash mode, we can simulate a fault on bus main 1. And I press OK. And this is a scenario which we have ArcFlash with ZSI study case. And you can see with ZSI implemented, we achieved faster tripping, which is 62 milliseconds. And we reduced the incident energy in this case to 1.845 calorie per centimeter square. And now let's change the study case, right, to use ArcFlash study without ZSI enabled. We do the same and simulate a fault on bus main 1 again. And we can see the tripping time or the fault clearing time of LVCB-main 1 is 0.3 seconds. And the incident energy is 8.927 calorie per centimeter. And it's level D. So with ZSI, we can achieve both coordination and faster tripping for ArcFlash as well. Let's summarize today's presentation. We learned what is ZSI, how ZSI works, how the ZSI graphic representation on OLV can help us to do protection and coordination studies, and how ZSI implementation in our system can help with coordination as well as ArcFlash studies. And hopefully you enjoyed this section. Thank you so much for attending. Thank you.